And our first example is going to be the hypotonic solution. So in a hypotonic solution, hypo means less. So we have less solutes out of the cell than inside of the cell. So first we're going to draw the cell. And then we draw the water. And the water is found outside and also inside of the cell. And represented in green, we're going to have solutes. This could be anything like salt, sugar. There's a lot of it inside of the cell. So due to the cell wall being semi-permeable, it'll only allow water to go in and out of it and not the solutes. So we have water going in and water going out. But over time, since there is more solutes inside of the cell wants to establish equilibrium with its surroundings. So there's going to be an overall net movement of more water into the cell. And over time, with enough water, the cell will eventually lyse, which is basically popping. So here we have lyse. And this is a hypotonic solution. And our second example is now going to be talking about isotonic solution. So again, we're going to draw a cell in red, suspended in a solution of both water, smaller molecule, and solvent in green. So with an isotonic solution, there's an equal amount of water inside the cell than outside. Solvent. And an equal amount of solvent. So because there's an equal amount of solvent and of water in and out of the cell, the net movement of water is actually zero. And what that means is that there's no more water going into the cell than out. It's equal. So the cell, in turn, is just normal, or the experiment, sorry. And this is called an isotonic solution. Iso meaning equal. So for our last example, we're going to be talking about hypertonic solutions. Again, red for cell. And it's suspended in a solution of water and solute. And then same thing inside of the cell, water and solute. But this time, there's more solute on the outside of the cell, which is what hyper means. It means there's an abundance of. So as a result, there's a net flow of water moving out of the cell. More out than in. Over time, the cell will eventually lose its form and it'll end up shrinking. And in the science classroom, we either call this shriveling, or more accurately, crenation. And this is a hypertonic solution.
So now we're going to use 3 real-life examples of each solution. So here we have a saltwater fish in fresh water, and fresh water is a hypotonic solution for saltwater fish. Hypotonic solutions have a concentration of solute, in this case salt, which is lower than the concentration of salt inside of the cells of the fish. If you were to place a saltwater fish into fresh water, their cells will have a much higher salt concentration than the fresh water that they are being placed in. which will then cause water to rush into them through osmosis. This will most likely cause their cells to burst and therefore lead to their demise. So in conclusion, fresh water is a hypotonic solution for saltwater fish, and saltwater fish should never be placed in fresh water.
A common example of an isotonic solution is saline solution. Here we have a man who is severely dehydrated, so he went to a hospital to get help. Normal saline solution contains 0.9 sodium chloride and is primarily used as IV fluid. When red blood cells are placed in 0.9 salt solution, they neither gain nor lose water by osmosis. Such a solution is said to be isotonic. Now we're going to show you a real-life example of a hypertonic solution. Here we have a snail, and we're going to pour salt on it. After a while, the salt on the snail is going to cause water from the inside of the animal to flow out of its thin membrane. The snail will then, after a period of time, start to shrink, shrivel, and eventually die, because the salt is very hypertonic to the snail.